Okay, Cal PC, Unit 3, Day 3, Office Hours. I'm going to go over the assignment. This is out of our old book from last year, which you may or may not have a copy of, or maybe you just don't want to deal with it. So I did upload the PDFs of the pages, and then also these are the solutions for all the problems, even and odd. So you should have checked those already. Those are online. But here they are again. You can pause it if you need to, and then. And this is kind of minimal answers. You should probably put some more reasons and stuff like that. So check it, pause it if you need to. And we're going to go over these problems. So problem 2 looks like a similar problem to what we did in class. In fact, I think it might be the same. 2 non-negative numbers chosen so that their sum is 1, and the sum of their squares we want to maximize, minimize. So we want to do sum of squares. So I would say, okay, well, we could call them the sum of the squares. Call one of them x and one of them y. So x squared plus y squared is what we're trying to optimize. And then we need another condition. So their sum x plus y equals 1. So then you could solve for one term as the other, y equals 1 minus x. Plug it into the other equation. And so there you go. We could clean it up. This is going to be x squared plus 1 minus 2x plus x squared. So s equals 2x squared minus 2x plus 1. We want to find a critical point, so we take the derivative for x minus 2, set it equal to 0, undefined. Solve. X equals 1/2 is your critical point. Endpoints for x, smallest would be 0 because they're non-negative. The largest would be when y is the smallest, and y is the smallest at 0. And it's possible they're both 0, so x would be 1. So these are your endpoints. And then you would make a little table. X 0, 1/2, 1. You plug them into the sum. X squared plus 1 minus x squared. So we get 0 squared plus 1 squared is 1. We get 1/2 squared plus 1/2 squared is 1/4 plus 1/4 is 2/4, which is 1/2. And if you plug 1 in, you get 1 squared plus 0 squared equals 1. So here's your max. And here's your min. And so part A said to find the as large as possible. So A could be the largest sum of their squares is 1 when the numbers are 0 and 1. 1 and 0 is the same thing. Okay. And we could say by extreme value theorem, by checking endpoints and critical points. So that's a good thorough answer with justification. Now part B says the smallest possible. So we say the smallest sum of their squares is 1/2 when the numbers are 1/2 and 1/2. by extreme value theorem. Checking endpoints or critical points. So this is the work I want to see. This is the way I want you to write your answers, justification I want. There you go. So that's problem number 2. Problem 16. So you guys can see that, I guess. Problem 16 says a church window consisting of a rectangle topped by a semicircle is to have a perimeter P. Find the radius of the semicircle if the area in the window is to be a maximum. So rectangle topped by half a circle. So like a church window. All right. And, so the circle has a radius of R. You have a base and you have a height. And we're trying to find the radius for max area. So the area is going to be base times height plus 1/2 of 2 pi r circumference. It would be good to get this down to less variables. So the base is actually 2 r's, right? So we could say, okay, well, the area is 2hr plus pi r. And then we need to, now this problem is a little more complicated because we don't have a value or a relationship between h and r. So we don't really know that. So I guess we're just going to write answers with letters in them. It says that that the perimeter of the whole thing is use p. So we're going to use that in our answer. So the perimeter equals p equals oh shoot, I messed up this. This should have been pi r squared. Okay. The perimeter is the base plus 2 h's plus 1/2 of the circumference. That's what I should have done there. Circumference 2 pi r. Keep making mistakes. So the halves cancel that out. And we replace b with 2r. So the perimeter p equals 2r plus 2h plus pi r. So I guess we want to get our area formula in terms of one variable, and we have this other relationship here. So we could solve for, h or r. I think it would be better to solve for h because r is a little more complicated here. So I'm going to solve for h. So I'm going to say, okay, well, 2h equals the perimeter p minus 2r minus pi r, and then we're going to divide both sides by 2. So that's your h. It's the perimeter minus 2r minus pi r over 2. So we're going to plug this back in to our area formula to get it in terms of one variable. So the area now is 2 times this, so the 2's cancel. I mean, we could go ahead and just write it. Okay, so the 2's cancel, and then we could distribute the r in. So the area equals PR minus 2r squared minus pi r squared minus 1/2 pi r squared. We could combine like terms, which as much as we can clean this up, probably better. So we have a PR. P is a constant, minus 2r squared, and let's see. Oh, this should be plus. I don't know why I changed that to a minus. It's supposed to be minus 1/2 pi r squared. Okay, so we finally got the area formed in terms of a single variable. P is just a number, so we're just going to have that pop up in our answers. So we're going to take the derivative. P is just a number, derivative PR minus 4r minus the 2 cancels out pi r. I'm going to say that equal to 0 undefined. And so then the radius, the critical points are going to be, we could move the r's to the other side, and then we could factor the r out, and then we could solve for r. So r equals p, whatever the perimeter is, over 4 plus pi. So this is your critical point. It's kind of gross. Do we have endpoints? Well, let's see. What are the biggest and smallest values of r? Could r be 0? If r was 0, seems like that's possible. You'd have a 0 area, but you could still have the perimeter. It would just be all h. And then what's the biggest r could be? Well, that would be the smallest h. And I think h could be 0, and then everything would be r, right? So if h equals 0, we go up here and say, okay, well, if h is 0, what is the r value going to be? So you multiply both sides by 2. You get 2r plus pi r equals p. You take the r out. This is a challenging problem. So it seems like the biggest r could be would be this. P over 2 plus pi. So these would be our endpoints. Now, I don't know. I think doing EVT is going to be challenging. We're just looking for find the radius of the semicircle if the areas be maximized. So we could try a table, but that might be tough. And plug the endpoints in and the critical points. So if you plug r equals 0 in, that one's easy, you just get 0. But then this one you're going to get, these are r values, you're going to get p squared over 4 plus pi minus 2 p squared over 4 plus pi squared minus pi p squared over 4 plus pi squared with an extra 2. I don't even know how to even say what that value is. We could do the same thing here. It's going to be p squared over 2 plus pi minus 2p squared over 2 plus pi squared minus pi p squared over 2 plus pi squared. So I could write these ugly expressions, but it's hard to evaluate these. So I think it might be better to just go with that first derivative test, even though it's harder to justify and often doesn't work. Let's just see what it does. We have one critical point, right? And then we could test a value like, I don't know, r equals 0. And if you plug 0 into a prime, you just get p, which is positive, negative. So it's going like this. So this is actually a good special case where we could say, okay, well, this is a relative min. And therefore, since it's the only one, it's going to be the absolute min. And so this is the location of the absolute min. So we're going to say the maximum area occurs when r equals p over 4 plus pi. And this is the maximum area right here, I guess. I don't know if we really need to write that. We're not going to really say, you could say extreme value theorem, but I really kind of relied on first derivative test to make it easy, make it an easy conclusion. So I'm just gonna stop there on that one. 17 says a sheet of cardboard 12-inch square is used to make an open box by cutting squares of equal size from the four corners and folding up the sides. What size square should be cut to obtain a box with the largest possible volume? So we have a square sheet, square. We're going to cut corners out of equal size and then fold up the sides to make a box. And it's open, there's no lid. So we got to cut these out. Okay, and it says it's 12 inches on each side, right? So a good picture. And we're trying to figure out what size squares to cut out. So to maximize the volume, so we're trying to maximize volume, length times width times height. I'm going to call these little dimensions x. Okay, so if these are x, and this is 12 minus x, 12 minus 2x, and this is 12 minus 2x. So the volume, the dimensions are 12 minus 2x, 12 minus 2x, and then just x is the height. So that's our volume. So if we multiply this out, we get 144x. We get minus 24 minus 48 x squared, and then positive 4x cubed. Now the nice thing about this, it's all in one variable. So we can take the derivative, 144 minus 96x plus 12x squared. And then we could try and solve this, set this equal to 0 undefined. Let's see if I can factor this. Now, is there a GCF we could take out? I think we can take a 12 out of everything. That's going to make everything easier. X squared minus 8x plus 12. And so then I'm going to factor this, hopefully. Pair numbers that multiply together get positive 12, so they've got to both be negative. Add together to get 8, so that's going to be a 2 and a 6. And so x equals 2 and 6 are the critical points. The endpoints, what's the smallest x could be? Well, 0, which is silly, but it's possible. And what's the biggest x could be? Well, you could cut it. You could make x go all the way, and everything's a corner, and that'd be 6. Because there's 12 inch sides, right? So if you made both of these go all the way in to where there's no side anymore. So these are your endpoints. So we're gonna do a table, plug in our volume, and we're gonna plug in 0, 2, and 6. So 6 is a critical point and an endpoint. Whatever, that's fine. If there's any critical points outside the endpoints, don't calculate them. So this is gonna be 12 times negative 2 times negative 6. Oh, this is weird. Oh, I'm plugging in the wrong thing. This is v prime. We want to plug them into the volume, which was 12 minus 2x, 12 minus 2x, and x. There we go. I made that mistake. Okay, so this is going to be 12 times 0 is 0, of course. Plug 2 in. You're going to get 8 times 2. So that's going to be 64, 128. If you plug 6 in, you're going to get 0 times 6, which is 0. So that's the other. And so here's your max, and here are your min values. I think we're looking for the max. So we're trying to find what size squares should be cut to obtain a box with the largest possible volume. So I'm going to say the largest possible volume of the box is 128. What are the units on this? Square inches. When and so the x is this 2 inch by 2 inch squares are cut from the four corners. I don't know, something like that. And then we're going to justify it. So we're going to say by extreme value theorem, by checking endpoints and critical points. So let's go through our answer. Good work. That one seemed nice after problem 16. That one was gross. Okay, let's try a couple more of these. Uh, 22 says a container with a square base, vertical sides, open top has been made from 1,000 square feet of material. So container, square base, vertical sides, open top. Okay. So square on the bottom. Not necessarily square vertically. It's not necessarily a cube. Okay. It's going to be made of 1,000 square feet of material. So that's the surface area of our material. It says find the dimensions of this hammer with the greatest volume. So we're looking for a greatest volume. Now I'm going to call these down here x and x because they're the same because it's square base. So I'm going to say the volume is x times h, or x squared h. So there's got to be another relationship to get this in terms of all single variables. So that's the surface area. So the surface area is there's an x squared on the bottom, and then there are four faces that are all xh, and it's supposed to add up to 1,000. So then we could solve for h or x. I think it's going to be easier to solve for h this time. I think it's going to be less messy, so I'm going to go with that. As far as the variables I chose, I'm going to solve for h. So if we do that, we get that. And I'm going to plug this in up here. So then our volume equals x squared times 1,000 minus x squared over 4x. So we could cancel one of the x's out. We could distribute this and make this a little nicer. So that's going to be 250x minus 1/4 x cubed. So here's our volume in one variable. So now we're going to find the critical points, take a derivative. So equals 0 and define. So let's see if we can solve this. 3/4 x squared equals 250. We're going to multiply both sides by 4/3. So x squared equals 1,000 thirds. We're going to take square root of both sides, plus or minus. So we just want the positive one because we can't have negative sides. So that's our critical point. Our endpoints. What's the smallest x can be? X could x be 0? X can't be 0 because then you don't have any surface area. And it says we have to use that. What's the biggest x can be? Well, what's the smallest h can be? H can be really, really short. And then that gives you all the rest of the material for h. So smaller x gets, or smaller h gets, bigger x gets. H can get tiny, 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 really short. And then I feel like to make up for it, x would have to get bigger and bigger and bigger. So can x go to like infinity or something like that? So this is a good example on that. I don't think we can do extreme value theorem on. We could try some ways of sort of mimicking it, but okay. So I mean, if we tried EVT, we can't technically do EVT, but let's just see what happens. So I guess we're going to go, we can say the limit as x goes to 0, because we can't actually plug 0 in, and then we got the square root of 1,000 thirds. And then I guess we could do the limit as x goes to infinity. And so if you do this as x goes to 0, this does go to 0. It goes to 0. And if you go to infinity, let's see. If you go to infinity, the volume, looks like the volume blows up, which doesn't seem possible. Plugging in the right thing for the volume. Yeah, I don't think we can go to infinity. I don't think that's the solution, but I just don't know what the other endpoint is. Now, if we plug this in, we could get, okay, well, this is 250 square root of 1,000 thirds minus, if you cube this, you get 250 over 12 square root of 1,000 thirds. So, I mean, we can try and clean this up. They're both kind of like terms. Does this go in here? 125 over 6. That's as good as you're going to get. And give this least common denominator. So that'd be 500, 1,500. So 1,375 over 6 square root of 1,000 thirds. Maybe that value. Now, here's the deal. Let's try first derivative test. And hope that this is a special enough case. It only has one critical point, right? That's really what we need. So you have one critical point, test a value. Now we have this endpoint 0 for sure. We could test x equals 0 in the derivative, and it comes out positive. So then it's negative. So it should be going like this. It should be increasing and then decreasing, and this is critical point. It's a relative min but it's the highest point, obviously. So it's got to be the absolute min location. And so they asked for the dimensions. Okay, so if you calculate this with your calculator, let's see. I tried it before. Let's see if I get the same answer. 1375 divided by 6 times the square root of 1,000 divided by 3 is, I mean, this is coming out 4183.991. I don't know if that's 100% correct, but so I'm gonna go ahead and let you off the hook a little bit here and not fully justify this, because justifying this for extreme value theorem is hard, but the dimensions for the greatest volume are square root of 1,000 thirds feet by square root of 1,000 thirds feet by, and then we got to plug this into this h expression up here, I guess. So that would be, I don't know, 1,000 minus 1,000 thirds over 4 times the square root of 1,000 thirds feet. And it's kind of ugly, but I guess something like that. I mean, you can clean it up a little bit. But, all right, that was tough. Okay, 42. Commercial cattle ranch currently allows 20 steers per acre. 20 steers per acre. On the average, its steers weigh 2,000 pounds. Weigh 2,000 pounds at market. Estimates by the Agriculture Department indicate that the average market weight per steer will be reduced by 50 pounds for each additional steer per acre added. Okay. How many steers per acre should be allowed in order for the ranch to get the greatest, largest possible total market weight for its cattle, all its cattle? So we got to come up with some kind of, okay, so total weight is going to equal number of steers times their weight, right? And it's going to equal based off their when it's 20 steers per acre, number of steers, get largest total. Do we know how many acres we have? Yeah. So the number of steers we have, I think we're just going to get a max weight for steers per acre. So we have 20 steers. If we add more, it's going to reduce their weight. So when there's 20 steers, it's 2,000. So if x equals 0, you get 2,000. But we subtract 50 for each additional steer. So that's our total weight. And so we could multiply this out. This would be this would be 40,000 minus 1,000x plus 2,000x minus 50x squared. So it's all in one variable. So total weight prime is going to be 1,000 minus 100x. We're going to set it equal to 0 undefined. And we're going to get x equals 10. That's your critical point. Now the endpoints, well, x is number of steers we're adding, so we could take away 20, possibly, right? And then the upper end, well, I guess one logical way of saying it is that their weight can't go to 0, right? So let's take the extreme case that their weight goes to 0 and figure out how many steers it takes to make them super skinny. It's 40. So that might still seem, impossible, right? But whatever. So these could be our endpoints. So I think we could do extreme value theorem here. Negative 20, 10, and 40. I'm going to plug it in a total weight. I like this factored version for doing the work in my head quicker. And then so if you do this, you get 0 times, doesn't even matter what this is going to be, but that's going to be 1,000. So it'd be 3,000. 0. If you plug 10 in, you get 30 times 1,500. So it'd be 45 with 3 zeros on the end of it. And then if we plug 40 in, we get 60 times a weight of 0, so that's 0. So here's your max, here's your mins. We just don't want to get negative total weight. That just doesn't make sense. So that's kind of how I determine my endpoints. No negative cows, no negative total weight. Even 0 total weight seems silly, but negative is horrible. So there's your answer. So we're looking for how many steers should be added per acre. So this is how many steers are being added. The largest possible total market weight is 45,000 pounds per acre, because we don't know how many acres. So we don't know the actual total market weight, but we know the max market weight per acre when 10 steers are added to 20 steers per acre. So, in other words, 30 steers per acre. By extreme value theorem. By checking endpoints and then critical points. So that one worked out. That was kind of a little interesting. I would, I'd avoid first derivative tests if I could. I was able to. And justifying this answer is way easier than justifying like a first derivative test like we did in last one. Now you could do first derivative tests on here, and I think it would actually lead you to the location of the absolute max. Okay, 56, little man floating a rowboat problem, which is a problem that we did last year. So man is floating a rowboat 1 mile from a straight shoreline of a lake. A town is located on the shoreline 1 mile from the point on the shoreline closest to the man. So let's draw a picture. We have a shoreline. You got your rowboat. It says that it's a mile from straight shoreline. A town is located 1 mile from the. Okay, so he's 1 mile out, and then there's a town 1 mile down, and as suggested in coming figure, he intends to row in a straight line to some point P on the shoreline, and then walk the remaining distance to town. So we say P. So you're going to row straight and then walk the rest. Now, one case is he could row this way, but we're not going to row backwards because that would whatever. To what point should he row in order to reach his destination in least time? If, and they give you two different situations, he can walk 5 miles an hour, row 3 miles an hour, walk 5 miles per hour, row 3 miles per hour. And then the other one is walk 5 miles an hour and then row 4 miles an hour. So that's an alternate problem, but we probably use a lot of the same work. So we're trying to minimize time. We want the least amount of time. So we got to figure out expression for time. So I don't know if you guys ever remember distance equals rate times time. That's stuck in my head. D equals RT. So then T equals D over R, distance over rate. So our time expression is going to be, I'm going to write it over here. Our time expression is going to be distance. Now we got to create a variable somewhere here. This is probably the best place to create the variable right there. This is x, and this would be 1 minus x. And then this would be the square root of x squared plus 1. Pythagorean theorem. So our distance rowing is the square root of x squared plus 1 divided by the rate rowing is 3 on the first problem, plus distance walking is 1 minus x over rate walking is 5. So there's your time function, and it's already in one variable. So then we could take the derivative, and we're going to get 1 half times this, so 1/6 x squared plus 1 to the negative 1 half times derivative what's inside. Don't forget the chain rule 2x. This is the same as 1/5 minus 1/5 x, so we're just going to get minus 1/5. And we're going to set it equal to 0 undefined. So probably want to clean this up a little bit. This is x over 3 square root of x squared plus 1 minus 1/5 equals 0 undefined. Now, undefined could happen here when x squared plus 1 equals 0, but when you solve for that, which I want to see, you get imaginary. So we're not going to use those. So we could also, by the way, combine these into a single fraction, which was kind of a common strategy. So you got to give them least common denominators, which isn't too hard. This would be 5x minus 3 square root of x squared plus 1 all over 15 square root of x squared plus 1. And then so then this, we already did this one right there. This is the top, so this would equal 0. So it's going to be 5x equals 3 square root of x squared plus 1. We'd square both sides to get rid of the square root. That's going to be 25x squared equals 9x squared plus 9. So that's going to be 16x squared equals 9. So that's going to be x squared equals 9/16. So we're going to take the square root of both sides, plus or minus. Plus or minus 3/4 are your critical points. Now, endpoints are going to be, what's the smallest x could be? X could be 0, and x could go all the way to 1. So these are your endpoints. So then you make a table, and put an x in and the time. And so plugging endpoints in 0, plugging, so we're not going to plug in negative 3/4 because it's outside the endpoints, and we're not going to go backwards. Plug 0 in here, get 1/3 plus 1/5. Least common denominator would be 5 plus 3, 8/15. If you plug 1 in, you get the square root of 2 over 3. And then if you plug 3/4 in, you get 9/16 plus 1 over 3 plus 1/4 over 5. And then 9/16 plus 1, that'd be 25/16. That'd be 5/4. That'd be 5/12 plus 1/20. So we could do least common denominator 5 times 12 is 63. So it's 25 plus 3 is 28/60ths, which is 14/30ths, which is 7/15ths. Now we could try and estimate these. Now these are clear. This is definitely smaller than this one. This one I'm not really sure, but on your calculator it is 0.471. On your calculator this is a little bigger than half, right? It is 0.533. These are really close. So let's go ahead and just use our calculator. 0.467. So this one is barely the minimum. Okay, barely the minimum. So then we're going to say the minimum amount of time, the least amount of time to reach his destination is 7/15 hours when he rows to a point 3/4 miles down the shore and walks the remaining 1/4 mile. Okay. Now I'm not going to write all that down just because the video is starting to get long. And then you would say by extreme value theorem, checking endpoints and critical points. The other problem, that's part A. Part B just makes a little tweak to it and just changes this, which just changes this right here. And so, similar idea, but the work is a little different. So I'm going to let you guys finish that. I mean, you could look at my work online too if you want, but these are kind of classic problems from last year too, these time problems. So there you go.